So where are we going with this? Our aim is to derive relationships or equations that we can use to calculate delta U, delta H, and delta S for real stuff. And this delta can refer to an end minus a beginning, an out minus an in. It's just a change in state variables. So far we can calculate them for the ideal gas. We can determine them for steam because we've got tables. Or thermodynamic diagrams, and that is in fact true for many other real components. But what about the missing link, and how were those variables calculated in the first place? And this is what we want to deal with in today's lecture. So let's consider a real gas, which is described by the equation of state referred to as the volume expansion of the virial equation. Just a reminder, this value Z in this context refers to the compressibility factor, pressure times specific volume divided by RT, which for an ideal gas is of course equal to 1. A different way of representing this equation is therefore to write pressure as a function of the temperature and the specific volume of that gas. This gas now experiences a change in state from pressure, volume, temperature 1 to pressure, volume, temperature at state 3. And we are interested in determining the change in its internal energy. Since it's a real gas, its internal energy is not only a function of this change in temperature that we observe, but it may also change because the pressure and the volume of the gas is changing. So for now we are only going to consider single components, and it's in the gas region, so it's a single phase plus 2, so our Gibbs phase rule tells us that 2 degrees of freedom for the system. So we can express that change as a function of 2 of the variables, either temperature and volume, or temperature and pressure, or pressure and volume. For this example, we are going to choose the temperature and volume combination. If we now want to consider the total change in the internal energy of that gas, we express it in terms of temperature and volume, we want to see how does the internal energy change with temperature if we keep the volume constant multiplied by the size of that change and integrate between the two temperatures, and the partial change of how the internal energy will change with volume while I keep the temperature constant and integrate between volume 1 and volume 2. So our main task is to write these two partial derivatives, express them in terms of stuff that we can measure in the real world. So we already know from the definition of constant volume heat capacity that that first slope is taken care of. That is the definition of constant volume heat capacity. So the slope that we are going to pay attention to is this: how does the internal energy change with volume if the temperature remains constant? Our first step in this procedure is to consider the equation of state, or the fundamental equation, where du is the subject of that equation. Our aim is to have du dv at constant temperature, so we are going to divide that equation by dv, but with this restriction that the temperature must remain constant. So this results in an equation for the partial derivative of u to v at constant temperature. So keep in mind that when we derive these equations, we want to get rid of all the slopes that are in terms of immeasurable thermodynamic properties, and we want to write all the slopes or the changes in terms of pressure, temperature and specific volume. So this one still requires some work before it is just in terms of those variables. And this is where we are going to use our Maxwell relationships. So if we investigate the group of slope relationships that we have, we notice that this one can be used to replace the change in entropy with a change in volume, rather with the slope of a change in pressure with a change in temperature on an isochord line. We can now substitute this new slope into our du dv slope equation, and this is the expression that we end up with. If we now substitute that back to our original total differential equation, we end up with an equation that can be used to calculate changes in internal energy with a change in temperature and a change in volume as a function of only constant value heat capacities and pressure, temperature, and volume expressions. The application of this equation for our gas obeying this equation of state, of course, the first part of the change, how internal energy changes with temperature while I keep the volume constant, this will be evaluated in exactly the same way that we've done previously. We've got the change in temperature to temperature final, CV as a function of the temperature. But it's this part of the equation that is now new to us. Group the terms together so that we have the change on this side and we know what expression we need to integrate from volume beginning to the final volume in order to calculate that part of the change. So what we're going to do next is we're going to substitute this whole equation for pressure. Instead of pressure here, we're going to take the derivative to temperature, while the volume is considered to be a constant in that equation, multiply it by temperature, substitute this whole equation for pressure in here again, and see what is the resultant equation that we then need to integrate. So after differentiation, we obtain this equation that we multiply by temperature, and this expression can now go back to replace this first part of that equation. And of course, for pressure, we can substitute that equation for pressure. And lo and behold, after all the trouble, we see that that part of the change between volume 1 and volume final results in 0 dV. So in terms of internal energy, this gas behaves like an ideal gas. The change in volume does not affect its internal energy. Please note that this is not a general result, it's only for this specific equation of state. The next few slides now show how to design alternative equations for dH and ds. Let's quickly go through this one. So if we want to write H in this case, it's expressed as a function of chosen variables, temperature and pressure. First, write the total derivative in terms of the partial derivatives or the slopes. Recognize that this is the definition of constant pressure heat capacity. dH dP at constant temperature still requires some work. Next step, this is really like a recipe that we can follow. Next step, fundamental equation where dH is the subject of that equation. Divide by dP with the restriction that the temperature is constant, and see if we can eliminate the partial derivatives that's in terms of entropy, enthalpy, and internal energy from the Maxwell relationships. Substitute that into our slope equation, and once we have the slope, we substitute back into our full derivative. And this is the resultant equation. And my recommendation is when you actually apply the equations is to group all the dP terms together. Do not try to integrate this part separately and that part separately, because it may just happen like in the previous example that the resultant equation, if you combine this in one single equation, is much easier to handle than these two on their own. An easy way to get an equation for the change in entropy is simply by combining the fundamental equation, substituting this equation that we just derived instead of dH, simplifying and making ds the subject of that equation. However, I would like you to try as an exercise to see whether you can derive this equation by starting with S is a function of temperature and pressure. So the full derivative of S is therefore equal to blah, 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 blah. See if you can get to this relationship. Smith, Van Ness and Abbott gives many examples where these equations are applied to liquids and solids. We will not be doing this in 2016.